just constantly churning out energy.
Yeah, incredible furnaces in space.
Right. And what scientists are trying to do here on Earth is basically build tiny versions of that to harness the same process, nuclear fusion.
Exactly. We hear a lot about it. The potential is huge.
For sure. But today, we're not just going to skim the headlines. We really want to dive deep into the fundamental physics challenges, the things right down at the atomic level that make fusion so incredibly hard to achieve.
That's the plan. Because, it's easy to think, just smash atoms together. Yeah. But the universe has these really fundamental rules about how tiny particles interact. So our mission today in this deep dive is to unpack those inherent barriers, the ones scientists are wrestling with based on, the actual science.
Absolutely. So for anyone listening who's thinking, okay, but how does it work? Why is it so difficult? Well, there's some amazing physics going on.
There really is.
We're going to explore that science, focusing on these core hurdles that come up in the scientific explanations, and hopefully get a much clearer picture.
Sounds good.
Okay, so let's start with the absolute basics. Fusion. It's about taking light atoms. Hydrogen's the classic example.
Yep, isotopes of hydrogen usually, like deuterium and tritium.
Right, and forcing them together so hard they combine into heavier ones, like helium.
And when that happens, a little bit of mass disappears, and boom, energy is released. That's Einstein's EMC, basically.
The famous equation, that's the energy we want.
That's the payoff, absolutely. Lighter nuclei fuse, make a heavier one, the result weighs slightly less, and that missing mass becomes pure energy, a lot of energy.
And this is the big but. Getting them to actually fuse, that's the really, really tough part.
That is the crux of the challenge. And the first massive hurdle you hit is something called the Coulomb barrier.
Okay, Coulomb barrier. So atom nuclei, they have protons, right? Which means they're positively charged.
Correct. The nucleus is the positively charged core.
So if you try to bring two of these positive things really close together, what happens?
They push each other away. Hard. It's basic electromagnetism, like charges repel.
Like trying to push the north poles of two strong magnets together?
Exactly that feeling. The closer you get them, the stronger that repulsive force becomes.
And that's Coulomb's law, isn't it? It describes that force.
It does. It tells us that this electrical repulsion shoots up dramatically as the distance shrinks.
And we need them really close for fusion, right? Like unbelievably close.
We're talking femtometers, quadrillionths of a meter, just mind-bogglingly small distances.
Wow. So getting past that pushback, that Coulomb barrier, it's a huge energy obstacle. It's why stuff isn't just fusing all around us all the time.
Precisely. It's like a really steep hill they have to climb, energetically speaking,
Whoa.
or find some way through it. They need to get within range of a different force.
Okay, but I hear it's not just the electrical repulsion. There's another layer.
Even as you're fighting the Coulomb barrier, another maybe less intuitive quantum effect comes into play. It's called the Pauli exclusion principle.
Pauli exclusion. Okay, now we're definitely getting into quantum mechanics territory. What's that about?
We are. So the Pauli exclusion principle is a fundamental rule. It says that no two identical fermions can be in the exact same quantum state at the same time.
Fermions. Okay, what are those in this context?
Protons and neutrons. The particles in the nucleus, they're both fermions.
Right.
So imagine you're squishing two nuclei together. The protons from one nucleus get really close to the protons from the other. Same for the neutrons.
Okay.
Because they're identical fermions, this Pauli principle basically says, hey, you can't occupy the same space with the same properties. It creates, well, an effective repulsive pressure.
So like a supercrowded elevator where identical twins suddenly can't stand next to each other.
No. That's actually a decent analogy, yeah. You try to force two protons with the same spin state into the same tiny volume. Quantum mechanics pushes back. Same for neutrons.
So it's another keep-away signal, but on a quantum level, between identical particles.
Exactly. Proton repulsion, neutron repulsion, on top of the overall positive charge repulsion. It adds another layer of difficulty at these extremely short ranges. And it's, profound. This rule is why atoms have structure, why matter doesn't just collapse.
Wow. Okay. So fusion doesn't break this rule then?
No, definitely not. Successful fusion happens when the conditions are so extreme that you can kind of manage these effects. You overcome the Coulomb force and deal with this Pauli repulsion enough for something else to take over.
This sounds like an incredible atomic wrestling match. So how do you actually win? How do stars do it? How are we trying to do it?
Right. How do we overcome these forces? Well, there are a couple of key strategies working together. The first one is probably the most obvious. Sheer heat. Extreme temperature.
In the sun, millions of degrees.
Exactly. Millions of degrees Kelvin. At those temperatures, the nuclei aren't just sitting there. They're zipping around at incredible speeds, just insane kinetic energy.
Ah, so they're moving so fast, they have a better chance of just smashing through that Coulomb repulsion, like brute force.
That's a big part of it. Higher temperature means higher average speed. More speed means some particles will just have enough energy upon collision to power through that repulsive barrier, or at least get much, much closer than they normally would. It dramatically increases the probability.
Okay, speed helps. Makes sense. But I've also heard there's a quantum trick involved. Something kind of weird.
Ah, yes. You're talking about quantum tunneling.
Tunneling. That sounds strange, like going through a wall instead of over it.
That's exactly the idea.
Yeah.
It's one of the most non-intuitive bits of quantum mechanics, but it's absolutely crucial for fusion, especially in stars. Even if a nucleus doesn't technically have enough energy to climb over the Coulomb barrier, there's still a chance, a probability, based on its quantum wave-like nature, that it can just appear on the other side. It tunnels through the barrier.
Like rolling a ball at a hill, and sometimes it just pops out on the other side, even if it wasn't rolling fast enough to get over the top.
That's the classic analogy, yeah. And the chance of this happening, the tunneling probability, it strongly depends on how high and how wide that energy barrier is.
Okay.
And guess what? Helps make the barrier effectively narrower from the particle's perspective.
High speed from the heat.
Exactly. The faster they're moving, the more likely they are to tunnel. So the heat does double duty. It helps some particles overcome the barrier directly, and it significantly boosts the chances for others to use this quantum cheat code, this tunneling effect. It's all tied to wave-particle duality.
Mind blown. Okay, so particles either smash through or sort of quantum sneak through. And then what? What happens once they've gotten past that initial repulsion?
Then the real powerhouse steps in. Once the nuclei gets incredibly close, we're talking just 1 or 2 femtometers apart.
That tiny distance again?
Yeah. A different fundamental force takes over completely, the strong nuclear force.
I mean, strong force. I've heard of that. It holds the nucleus together, right?
Precisely. And at these ultra-short distances, it is overwhelmingly attractive. Way, way stronger than the electromagnetic force that was pushing them apart.
So it's like they struggle and struggle against the repulsion, maybe tunnel through, and then suddenly, wham! This super strong short-range glue just grabs them.
That's a great way to picture it. The strong force just takes command, overcomes any lingering repulsion from Coulomb or Pauli effects, and binds the protons and neutrons together into a new, heavier nucleus, like helium, for instance.
And that binding process, driven by the strong force, that's what releases the energy.
That's it. The energy comes from the rearrangement and the binding under the strong force. The new configuration is more stable, has less mass, and the difference is released as energy.
So, wow, it's not about ignoring physics rules. It's about creating these absolutely extreme conditions, the heat, the density.
Generating speed, enabling tunneling.
So that you can get the nuclei close enough for this incredibly powerful but very short-range, strong force to finally win the tug of war.
You've got it. Fusion is this incredibly delicate dance. You need the heat and speed to overcome or tunnel through the electromagnetic and Pauli repulsions, just enough to let the strong nuclear force take over and do its thing.
Understanding that really highlights why building a fusion reactor is such a monumental challenge. It's not just about making things hot.
Not at all. It's about controlling plasma at millions of degrees under immense pressure or with incredible confinement to orchestrate this fundamental physics ballet at the nuclear level. It helped you appreciate how stars work and why replicating it here is, well, taking some time.
Definitely. Okay, this has been fantastic. Let's just quickly recap the main hurdles and helpers for everyone listening.
Sure.
First, there's the Coulomb barrier, the basic electric pushback between positive nuclei.
Yep, like charges repel.
Then adding to that at close range, the Pauli exclusion principle, this quantum rule that says identical particles like protons need their own quantum space.
Creates a repulsive effect, yeah.
And the keys to overcoming these, number 1, massive heat, millions of degrees, to get particles moving incredibly fast.
Gives them energy to potentially power through and increases the odds.
And number 2, quantum tunneling, this amazing effect where particles can sneak through the barrier, helps significantly by those high speeds.
The quantum cheat code.
Until finally, if they get close enough, the super powerful, short-range, strong nuclear force takes over, binds them together, and releases all that fusion energy.
That's the sequence in a nutshell. Overcome a repulsion, enable the strong force.
Brilliant. So thinking about all that, all these fundamental physics hoops that nature makes us jump through, What feels like the biggest remaining hurdle for making fusion power practical, something actually usable here on Earth? Is it just hitting even higher temperatures or densities reliably? Or are there maybe other physics puzzles still lurking that need, a breakthrough? What keeps fusion scientists up at night, fundamentally speaking?